line of best fit. So now that we know what the correlation is, we could when we have a correlation, we could find the line that fits the data the best. We could try to find the equation for that data set. So let's look here. We have this data. It looks like it's positive. It's going up. So what we do when we find a line of best fit, we try to find a line that kind of goes through the data evenly. So you're not trying to touch the line. You're just trying to kind of get through the data as evenly as you can. So like a line like this kind of hits the middle of all those data points. And then what you do is what we've been doing since you're in Algebra 1. You try to find the equation for that line. Right, there's a couple ways to find the equation of the line. You can do slope-intercept form. I always like to do y minus y1 equals m x minus x1. Point slope form is always my favorite. Right, and to do this equation, all you need is to find the slope. Well, you have 2 points. Look at your graph here, right? You want to find points that you don't care at the original data at all. You just want to find points that touch your line. So like this one happened to be something from the original data, but that doesn't matter at all. Like I might even use, let's say, like this one. Kind of crosses nicely, right? There's no data there. It's just it crosses my graph nicely. So use those 2 points, find the slope, plug one of the 2 points in for x1 and y1, and you got your line of best fit. IB likes to use a point called the mean point. I've never seen this on a test, but it's in the book. All that is you find the mean of your x's, the mean of your y's, so you get all your x's, average them out, and you get a point right there. And that's the point they use for x1 and y1. That's what IB likes to do. But again, I've never seen it on a test. So let's move on. Let's say I give you this data right here, right? So number of visitors and the average temperature per day at the beach. So by looking at it, it looks positive, looks moderately positive. So if I was trying to find a line of best fit here, all I do is just draw a line. Remember, it's an estimation. There's going to be no one right answer. Ooh, that's a bad line. Let me erase that because that's bad even for me. Try to find a line that kind of goes through that data kind of evenly. Oh, let's try my best. Right, so I have that. That's my line of best fit as best I could try. If I want to find an equation for that, I'm going to do y minus y1 equals m x minus x1. That's always how you find an equation of a line. You try to find 2 things that cross nicely. Like, even with my terrible graph here, down cross kind of nicely, and down kind of cross kind of nicely. So I would use those 2 points to find the equation of the line. Right, and once I do that, I don't know what I'm going to get. Let's just make something up. Now there's lots of things I could do. I know what the temperature is, right? X is my x value, so that probably should be an F instead of an X, because temp. So I could plug in the temperature, figure out the number of people are going to visit that day. Or, here's my Y. If you give me a number of visitors, I could tell you what the temperature is going to be. So, very useful information. Let's move on. The least squared regression line is actually the exact same thing. It's the line of best fit, but done by your calculator. That's the only difference. So it's done. It's a different type of program. It's a program that does it. So it's essentially the same thing. It's a line of best fit, just done with the calculator on calc. So let's talk about how to do that right here. So you gotta bring out your calculator. Here's mine. It's actually very similar to the thing we just did right here. It's that again, just now with this information. So we're gonna go stat edit, our favorite thing to do apparently. We're gonna clear out our data. Type in the new data. 150, 200, 250. Located short. 17.7, 20.4, 22.0, 25.0, 26, 27.8. So you have all your data in there, and it's just like finding the R. What we're going to do is go to get out of this, go to stat, calculate, and we're going to go to linear regression. That's how we're going to find our least squared regression lines. L1, L2, yeah, grams and centimeters. Again, no frequency list. You see, that's not a frequency list. That's just L1's a different variable. So request is if you want to graph it. We're not going to do that right now. You can calculate it. And that's our equation. So see, y equals ax plus b, and they give you what the a is, use 3 sig figs, and they give you what the b is, and they even give you the r. This one's a very strong correlation, 0.99. It's almost perfect. So our thing's going to be y equals 0.040 x plus b. So we have y equals 0.040x plus b, which was, I forgot, 18.1. Now I'm probably going to use the correct units, so it's actually going to be my x, this is my x, this is my y. So I'm actually going to be, the length is going to equal 0.040 w plus 18.1. And that's how you find a line of best fit or a least square regression line that gives you for your data there. And again, once you have this, the possibilities are endless. I could plug in a weight of a sternogram and figure out how long it's going to be. I could plug in the length and figure out the weight. Right? All that good stuff. I could figure the correlation, which in this case was 0.9, so very strong positive. All that good stuff. I've been doing it, mine's on the TI-84CX. It's done the exact same on the TI-84. If you have a Casio, I could give you how to do it on there, and I can also give you the TI Inspire, but I hate the Inspire. Don't buy the Inspire. Okay, let's go on to another example. Steve wants to see whether there was any relationship between the temperature when he leaves for work in the morning and the time it takes to get to work. So he collected data over a 14-day period. Draw a scatter diagram of the data. Again, I'm just my calc. We're gonna do all this in our calculator. Calculate R. Describe the relationship between the variables. Is it reasonable to find a line of best fit in data? Explain your answer. So let's do this. I'm gonna plug all that into my calculator first. All right, so I get my calculator out here. I'm gonna save you the trouble. I'll do it off screen. So there I go. All the data is entered in. Let me cover up some of this information here. So first let's draw a scatter plot. So remember the way we do that, we go to second stat plot. I already have it on and I turned it off. I probably should have. Bad manners in my case. L1, L2 all in there. My mark's fine, my color is fine. I'm hit graph. Again, now that data, I could kind of see it, but to make it better, let's fix the window. The easiest thing to do is put zoom stat, zoom 9. And then now I could see a better correlation. And that looks like a terrible correlation, personally. It looks very bad. So if I could drag this over here. It doesn't work like that. Well, whatever. So keep that picture in mind. So if I was going to kind of draw it, I'm not sure about you guys, but I see this. So I don't really see a correlation. But let's check. So now we're going to calculate R. Now we're going to calculate R just like find the least square regression line. We're just going to get out of this. We're going to go to stat, calculate, linear regression, L1, L2. Again, no frequency, so that's all good. So I'm going to leave my frequency blank. That's very important. I don't need to graph it, so let's go to calculate. And R is a negative 0.42. Not as bad as I thought, actually. So my R is negative 0.42. That's still weak, but it's a moderate. It's not like, I thought it was going to be close to 0, but it's still weak. It's a negative weak. So here's my B, this is my R. For C, describe the relationship between two variables, that's all you have to say is weak and negative. They always want, is it a positive, negative? And then what's type of correlation? Is it strong, weak, none, all that stuff. Is it reasonable to try to find a line of best fit for the data? Explain your answer. I don't think so. If you look at our graph here, right? I mean, it could, but it's a weak. You could. It won't be a very good line of best fit. Well, that's my answer. Before I move on, I want to go back and look at our equation here. So based on our least square regression line, I got this equation: y equals negative 0.31x plus 46.4. So y equals negative 0.31x negative 0.31x plus 41 plus 46.4. Now remember, we could do a couple things with this. This probably should be, X and Y is fine. I could plug in my temperature into here and I'll get out minutes. I could plug in a minute and get the temperature out. Now I'll tell us right now. We're going to talk about how good of an estimate this is going to be. Like if I plug in a number, let's say 30 for my temperature. I could plug in and get a value. Is that going to be a good estimate or bad estimate? What if I put a number in like 60? Right? Now there's a difference between those numbers. One of them, if you notice, kind of falls within the data set here. 30 falls between 35 and 28. 60 is way off. So check, that could kind of give you a hint which one's going to be good, which one's going to be bad. But let's talk about this more in detail. Interpolation, extrapolation. This is all about how good of an estimation your data is when you find the equation. So this picture is all you really need. Anything that falls within your min value, which we have right here, and your max value is called interpolation, right? Inter. So right, it's in between your data set. That's interpolation. That's right. It falls in between your data set. That's the one that's generally going to be a good estimate, because it kind of falls within your data set, right? So it's going to be a good estimate. Now, extrapolation falls out. It's all the data falls outside of. You notice right here how if you're going to estimate something that's lower than your lowest value, or you're going to estimate something that's higher than your highest value, we call that extrapolation. So outside your data set. And this is the one that tends to be a bad guess, especially depending on how close you are, how far away from here. If you're guessing something that's really far away from your data set, it's going to be a terrible guess. If you're guessing that's pretty close to it and you have a really high correlation, then it's probably still a pretty good guess. But most of the time, the general idea is extrapolation to be a bad estimate, interpolation to be a good estimate. So intra is, again, when it falls in between your data set, good estimate. Extrapolation is when it falls outside your normal data set. It's a little too high or a little too low. Then generally not going to be a very good guess. And that's what you can see right here. As a general rule, right? Interpolate between the poles is good, is reasonable. Outside the poles, extrapolation is unreasonable. So let's finish this off with a quick example. The table below shows how far a group of students live from school and how long it takes them to travel there each day. So distance from school, time to travel to school. They want me to draw a scatter diagram using my calculator. We're going to find the equation of a line and they are on the calculator. And then we're gonna solve this with our new information. We're gonna solve this little question C here. So let's do this on our calculator. Again, I won't bore you. I'll plug this in right now, and voila, all the data is entered in. So I'm gonna cover up this space right here on the side. So first thing, draw a scatter plot. So again, go back to your stat plot, turn it on. I left it on. I should really stop doing that. Then you go. I have it all listed: L1, L2. I'm hit graph. Again, you want to fix your window every single time, so zoom 9 because we're doing stats. And I guess like that looks like a super strong correlation. Very strong, I would say right now. Right, so my A here looks like a really strong correlation. Now B, use technology to find the R in the equation of the least squares line. Remember, we actually do the exact same move. You get out of this, you go to stat, go to calculator, you go to linear regression. L1, L2. Again, there's no frequency list, so leave that blank. That's for graphing. We don't need a graph, so let's skip that. Go to calculate. And there's our equation. Y equals 2.17x, I'm rounding 3 sig figs, plus B, which is 1.37. So 2.17, 1.37. So we're going to have, I meant to do that down here. 2.17, I think now, x plus 1.37. So that's my equation. I've told up the R. R is 0.993, which is very strong, as I suspected. 0.993. So, all right, we have a very strong correlation. We have our equation here. So there's A and B. Now C says Pam lives 15 kilometers from school. Estimate how long it takes Pam to travel to school. So okay, think about this, right? She lives 15 kilometers. That's the x value. So we're going to plug that in for x. So I'm just going to go y equals 2.17 times 15 plus 1.37. Just use a calculator. Let's clear this. 2.17 times 15 plus 1.37. And I get 33.92. So it's going to take about 34 minutes to get to school. Now B, comment on the reliability of your estimate. Now remember, all we care about is what we're plugging in. If that falls within our range here, then it's going to be a good estimate. If it falls outside the range, if they want me to estimate how long it takes for her to get to school, she lives 100 miles away, that falls 100 kilometers away, that falls way outside the range, so it'll be a bad estimate. This one, 15, falls within our data set, so we're going to call that interpolation, and it's a good estimate, or it's reliable. And that's interpolation, extrapolation.